So before start, I mean, it's a long day. So what's left will not be easy as tomorrow. So maybe I give you two exercise in case you don't want to listen to the lecture. So this is exactly what I mean, the ranking sample convolution. So if you have two functions like that, you just make the product of their coefficients. You get this in. The other one is a continuous analog of the first one. And of course, both of them can be proved by a very nice method. You can prove directly by hand. First one, of course. Second one, you have to invent something. But I guess everybody knows how to prove the second one. I mean, the method you need to invent is the convolution. You need to take the Fourier transformation from one side to the other side. So in this case, the Fourier transformation is a Mellin transform. So you have to apply the inverse Mellin transform. So it's funny. So first one, you prove by elementary method. After you prove the second one, you suddenly realize that first one you should prove by some fancy method. So this is basically Mellin transform from this side to the other side. You have to write this thing in a very coherent way. I mean, how can you write a DAN? So this is a group. You have two groups you work on. Okay, so that is all the key thing used in today's lecture. But probably I will not go this detail. But that's basically the down to the earth computation is these two. So to see this thing, this is exactly the error function. We know that the zeta function at infinity of S. So if we write a zeta function as a product of zeta v of S, you should Riemann zeta function. That is infinity. And of course, this is the finite part. Okay, so of course that's a GR2. Everything is a GR2. So the reason I put it twice here is usually the convolution from negative infinity to positive infinity. If we replace everything from positive infinity to negative infinity, of course you need to require this phi I to be even function. That is 2 will disappear. Probably, I mean, maybe if you're not very happy what I put 2 here. 2 here because I cut the integral from negative infinity to positive infinity. Okay, so yesterday, so we just recall what we have done yesterday. That we started with a new form. And for U naught of n, of course, everything we have this is a totally real field. And this n is the idea of OF. And this form, it can be viewed as a differential form in the Heister. You can think of this stuff this way, as a differential form there. Then another thing we think about anti-cyclotomic character, ring class character. Of course, then you get the induced representation of the Galois group. It's a representation of f bar of f to complex number. From these two, we can make up our error function. That is Ls chi f. Usually I write everything the opposite way than the number theory is right. And the reason is after you work on automorphic form, S is always the beginning. So, so this is will be Rankin-Selberg. Convolution. So I assume this one assume this one has a conductor of chi, then this one will be conductor, the induced resistance will be conductor D equals C, then this conductor will be C squared times D will be big D. So the big D is the conductor of induced representation. C will be a conductor of the character. So C character as a ring class character of something, the Galois representation of K bar of K. So K of F is a totally imaginary quadratic extension. So this is a convolution, this is L series, this conductor will be n times D square actually. And you have L series will be -1 to the F sigma nk L2 minus S. Oh, there's a conductor. ND 2 minus 2S. Maybe yesterday I lifted one of them because always. Then you have L2 minus S chi F. Then from the sigma of nk, then we have construct. If this is order, doesn't matter. We can construct the quaternion algebra with ramification said to be exactly sigma nk take one place out. So from analytic data, finally we come from something algebraic. Now from this algebraic data, we can make up a Shimura curve that is G of F positive, Poincare hyperplane, G of F H over U and K. So this is Shimura curve of NK type, and this G is algebraic group B cross mod F cross. The UNK is the image of RH cross modulo OF cross. This R is order of B of discriminant, relative discriminant, with respect to the canonical quadratic form there, equals N and R contains OK. As I said that, if you think, if at the very beginning you make a pretty silly case, a case F plus X, F is totally split, then everything you get is something called alkyl order. That is a classic case. Then the main theorem yesterday we described is that the main theorem we did yesterday is that this Jacobian of X will have an abelian variety AF is unique such that the L series of this abelian variety is exactly given by the Hilbert modular form. So these sigmas are all conjugates. So in case, for example, if the coefficient of F is rational, you will end up an elliptic curve defined of F. Conversely, I mean, in most cases depends. Conversely, start with the elliptic curve defined of Q. If your base change F, if your F conversely, if your E over Q, we know it's modular, F of Q is solvable, then we end up, then what you can prove that E of F is also appeared in this picture. What I mean that this will be associated to certain form of F. This will be associated to a form associated to f of q. In this way, the theory, the formula we will describe in this case applies to elliptic curve of q. But the only thing we can prove, of course, meanwhile, the theory of homomorphic forms can only handle the case f of q is solvable. If f of q is not solvable, you cannot, it's a conjecture. So what that means, the conjecture is if an elliptic curve is, if some abelian variety is a modular of a field, the still modular when you make best change. But here, we only know when this is solvable. So not only that, we actually know the parametrization. We can describe the parametrization from X to this AF. This is given by some notion of admissible parametrization. So it's X, so admissible means that you want pi psi to be torsion. This psi is something called Hodge clause. And this is nothing new. If X is split, if B is split, this psi is really the class of cusp. So it's exactly the analog of what we do in the classical case. Okay, that's what we have done yesterday. So today we want to continue. So we want to talk about, I don't know what the number is, the CM points. So what I really mean is the CM points by K. So you have this upper plane, you have G over F. This is the curve you get, G over F. Positive means the determinant is positive because you have a matrix. The matrix will, only the positive determinant keeps the upper plane there. Otherwise, it will map upper plane to the lower half plane. All these U and K is X of NK. So CM points I really mean, so point X is CM points, is supposedly represented by a 2 point. One is H, one is G. There's a CM by K if and only if the stabilizer of H inside of the GF of plus is a torus. This one inside, this one usually is trivial. This one is conjugate to the standard torus T. Okay, so I have not yet talked about T. T is algebraic group K cross modular Q modular F cross. Inside is G. Okay, maybe I should call it T CM point. Well, all these points are conjugate each other, actually. There's only one orbit. This definition probably is not really that great. So I should say it's not really, should be isomorphic. Isomorphic to not necessarily this one, but this implies the conjugate to this T. So in other words, the conjugation of this thing has only one orbit. Since this is the case, so what do we do? So we can fix one point. Fix the ZH 0 inside the plane. This one be fixed. Okay, let H0 be the upper plane, be in the upper plane, fixed by T. T of what? T of R, doesn't matter, something. And this one is unique. Then you see that is all the KCM point is can be written as G of F plus, this is conjugate, so G of F plus times H0 times G of AF divided by U. Right? I mean, so everything is represented by this element, but this thing is fixed. So this is isomorphic to where you have a map to this G over F over U. Then you will, if you compute this side, it's exactly nothing else, just T of F. So T of F is this one is K cross of F cross. The nice thing, this is the same point. This is every KCM point is inside this way. The nice thing is the following thing. The theorem is the Shimura theory or theory of Shimura varieties is saying these KCM points are all defined in this KAB, the maximum abelian extension. Not only that, the Galois action, moreover, the Galois action, I mean of the Galois KAB over K or even over Q, doesn't matter, over K or over F, for example. This is given by the left action, the left multiplication of n normalization, give another group, nt of AF. So I will explain that. This nt, the normalizer of T in G. So nt contains T, and then you have a group. It's a two elements group. So this is very nice. So when you describe the Galois action, it purely becomes geometric action. There's no after a while you don't need to go back to the algebraic side at all. Everything is geometric. So now I define a sentence, something called a Hingnan points. So the Galois orbits, I mean, that doesn't matter which Galois orbits I talk about. Maybe I just Galois orbits of this for this group, for the Galois, for T, okay? Okay, I mean, this is also the T of F, of T of F. It's given by, it's smaller because the Galois orbit acts on this sand. It's you factorize a little bit more. So this is given by G over AF. What? What?
Is this with K up or something smaller?
Something smaller. It's a quotient group. You're right. It has something. It's complicated. You have to. This is really. Maybe I could define a name. The ring class extension. H infinity. The ring class, maximal. So I mean, it's the join of HC. That's better. Okay. So this is given by the T of AF modulo U. So this is nice because this one is totally become local thing. So Galois orbits can be described as local thing because everything is here. There's no global thing here at all. Everything is local. So you can write down, it's just a product, some restriction product of T, FV, G of FV, of UV. So it could be nice to classify, to understand that set. This is one side. Second side, the second description probably is very important. There's some invariance. The invariance is the following thing. Suppose X is the CM point and represented by this H0 of G. So what you can do, you can define a map phi G. You can think about this order. You can think about G of this order. This one intersects with K. Well, I mean, I have it must be what do I really mean. This is elements in ideas. Probably put a head there. This will be an order in K. So it must be equal to something O of C. So this C is a conductor of X. So if you like, you can view this OC as anamorphism of X. So all these CM points somehow is ordered by this OC. So these KCM points is also the disjoint union of the C, the KCM points of conductor C. Okay, so you have these, you classify these points there. So when C is trivial, so this is something we usually call the Hinton point. When C is non-trivial, I don't know how can I call that. So basically, if we fix the character chi, you fix the character chi with the conductor C prime to n, then you can define, so what's going on? This set is quite complicated. And when C is not a prime to n. So when C is a prime, if C is a prime to n, this set actually is very nice, very easily to describe. Then this is K-sim points of conduct C. In that orbit, the modular is Galois extension, this Galois action. Galois orbit is actually exactly has 2 to the s orbits, Galois orbits. The 2 to the s is the orientations. This s is number of v of the place divided by n. So in other words, it's orientations. Depends on orientations. So at each place v divided n, you have 2 orientations there. So you have many choice. For example, for simplicity, we can choose a positive orientation. What do I mean the positive orientation? All these things are relative. So remember, we have a beginning. We started with the embedding of k inside. So let YC to be the one point there, one orbit, one CM point with positive orientation. The same orientation as the point represented by H0 and 1. Okay? Then you have a started orientation. The reason I do that is because when you do your cells or whatever, or Euler system, you want everything to be one system. But this doesn't depend on the choice. You can pick up the other system. Different orientation will give the same result. The difference is given by a torsion point. So you just fix one. And this YC also is not a canonical. I mean, it's difficult to say which one YC is good. You just pick up one point there. So I define, let me give a name up. My Y will be use something else, let's call it XC. So let me say X chi will be summation chi of T XC of gamma inverse. This is gamma in the group, Galois group of this HC of K. So these are we are called chi-Hingden points. Hingden divisor. Or cycle, whatever. So later on, we will work on different variety. Why I call it Hingden? The reason is, well, I have many chi divisors, but this C is a minimal conductor, exactly as a chi. So when I call some point Hingden, that really means I want to be level, a conductor as small as possible. This C is minimal. You can't have anything smaller than that because this chi has a conductor C. You can raise P, for example. That's exactly what you need to do for Euler system. You need to raise that. But C is minimal. C is the starter one you start with. So I can divide chi-Hingden divisor instead of defining the Hingden point. Okay, so I have this X there. I have a map AF. Of course, this is only defined over. I mean that when I everything I tensor with Q, then this is nothing. You can define this way or other way. There's no big problem. So I get this XC here, and then I get a point X chi here. I get a point Y chi. This Y chi is a point in AF, HC, tensor with a complex number, take chi component. No, maybe I should not do that. I can do this one. Or maybe I can do even more refinement. The refinement is that I can define this Y chi will be the summation of Y chi F sigma, O sigma. Now we have the formula, the main theorem of the lecture, the Gross-Zagier formula. So recall that we have this L series of this S chi F. This has a function equation whose sign is negative at 1. So in other words, this will be 0, and this one will not be 0. I mean, this, I don't know if it's 0 or not. This is the basic thing we want to do. So the formula is 2 to the g plus 1 divided by square root norm of d, the times the norm f square. Now we explain what I mean the norm square. The times the narrated hard pairing y chi f, y chi f. And this narrated hard pairing is defined, the base is f. It's always some kind of, some people, like in Gross-Zagier's paper, the base is k. If base is k, then you have to remove 1, 2 here. So when you define the pairing, narrated hard pairing for Jacobian, you have to pick up a field to start with. I pick up f there. The pick up f there, my 1 here has a lot of meaning. You will see what's going on, why I have need a 1. If I don't have 1, I have some trouble. So I explain some notation. So this norm of D is just the norm from this K, F of Q of the divisor D. Okay, this is nothing. It's not that hard. This f squared, well, it's just integration I over 2 to the g's power, the integration of the omega f, wedge omega f bar, and x naught of n. Okay? So I didn't renormalize by pi here, for example. And I needed to say something about the narrow height pairing because so many different definitions. I needed to make things extremely canonic. So what's going on is this Jacobian, usually narrow height pairing is with from 1 to the dual to the complex number of f bar here. So the definition is very clear. If you pick up a point here, people pick up another point there, this one will give you a line bundle. L1 is a flat bundle. So you can pick up certain flat structure. So you make it a bit flat, then make the degree of this thing. So this is a pairing. Negative one will be x or y. This is a narrow height pairing. So in our case, it's a self-dual each other. So you pick up a canonical self-dual to J of f bar. This canonical self-dual, I mean that this way. The canonical self-dual is the following thing. So J f bar, of course, is called pk 0 of J, define of f bar. Then this one have mapped to pk 0 of x f bar, but this is equal to J f bar. Okay, so this is what I mean, the narrow height pairing. For example, I didn't really use the theta divisor explicitly. But if you prefer to define the height pairing by ample divisor, then there is a factor 2 there. Because somehow there's a duality is always when you dual back, dual push forward, pull back, you get some factor there. So I will not, that's exactly what I mean, the height pairing. Okay, so everything explicit. Maybe one thing you will not feel happy is that this thing lives in, if you compare with the Birchson-Dye conjecture, this thing should be a period. But when I compute that one, this is a period on certain middle cohomology of the quaternion Shimura variety rather than the Shimura curve. So there is probably the better formulation, the different formulation you can get. If you want to forget, if you forget this thing, forget the fact, the gamma function, then you can get a different thing. You can get this one, okay, no infinity. You can get a formulation which is very similar to that one, but this one you get a symmetric error function. 3/2 symmetric error function of f. This one, you not only forget the gamma function, you also forget the fact which divide the n, whose square divide n. If you do this thing, then you get a probably better formula of h to the g, then times the 4 times the discriminant k of f. I guess that's it. And divide square root of d. Then get y chi f, y chi f. This thing is good because there's no gamma functions inside at all. Everything is, so you know the transcendency very clearly. So this invariant, for example, is totally isogeny invariant. If you change it, it doesn't depend on the thing to choose. Well, now I talk about the even case. So what happened? Even case. So the sigma nk be even. That's somehow it's a better case because it's even. So I don't need to pick up the Archimedean place anymore. So you simply pick up. So simply take is B such that the ramification set of this B will be sigma nk. But be careful, this thing contains all the Archimedean plates. So your quadratic algebra you get is definitely the quadratic algebra, totally definite. And you will still have a Shimura variety, but dimension of Shimura variety is 0. So you still have x of the g f. I mean, that doesn't matter. Everything must be positive because it's totally definite. You have nothing here, the g of f of the u and k. Now you have the trouble to define CM points because this thing is too small. Well, you define CM point. The CM point does not live in variety anymore. The CM point still will be, you define the CM points, KCM points, to be the TF of G of F of the U and F. Instead, I mean, in the classic case, we just, I mean, in the dimension 1 case, we just treat this is a subset of that. Now, in this setting, this becomes a quotient set of that. So the set of CM points is more than the points of variety itself. So you get a map there. Well, I mean, that's it's fine, but of course, sometimes psychologically, you wouldn't feel very happy about this setting, you know. So what do you do? Like the Gross did it. He inserted something here, like a projective variety here, to make this variety to be high dimension. But of course, every fiber is very simple. It's just a projective space. You can do that. There's no problem, right? I mean, but it doesn't really help. So then what's going on? So this is the CM points. Let's give you a name called C. So you have a C mapped surjectively to X instead of embedding. Here, well, we want to have a theory like a abelian subvariety. This is Eichler-Shimura theory. But recall that before we do Eichler-Shimura theory, we have something. I have found a canonical form. So this is a canonical form. This is share same eigenvalues as f. So this is a form. So here we have this CM divisor x chi. So I divide is a pi. So now the Gross-Zagier formula is given by L1 chi f equals 2 to the g, no plus 1 anymore, divided by square root norm of d, divided by times f squared. The same thing as exact same definition, nothing changed. Now this hard pairing is replaced by this thing. L of f prime. This, let me try to write something better way. F prime has a pair with y chi, it's x chi, whatever, square, divided by norm of f prime square. So what do you mean the pairing? So pairing, this is x chi here. This is a function here. How can you make a pairing? The pairing is a silly pairing. Just put back your function here. Then you just take so the pairing is really given by quite a simple way. So here, what do we do with CM points is somehow play the rule of the distribution. That is the kind of distribution, I mean, you see from work of Puget, but here we make extremely explicit. So there's a y chi, the x chi, and the f prime. This pairing is simply nothing in the Galois group of HC of k, gamma inverse of sigma f y xc sigma prime. This norm f prime square is computed. It's just a summation, f prime of x square for x in the variety x. So everything is extremely explicit. And this philosophy is very, very important. You can view this phi prime as the cutoff of your divisor. And on the other hand, you can think the CM divisor is a distribution on the function of varieties. Okay, so this is the finish, the statement of the result. But I could go on for the proof. But it's very, very important to extend this theorem to non-holomorphic forms for both the proof or for the application to Andreev-Otto conjecture. So I will stay a little bit about the Gross-Zagier formula for non-holomorphic form. So basically, it's important for proof. Even though I prove something holomorphic, I need a non-holomorphic thing because I need somehow what do you do in the theory of automorphic forms? That of course there's new forms that are very rigid. You cannot deform one new form to other new form. But the local facts are in the continuous family. The local facts is lambda, it's a complex number, so you can continuously move them. So somehow the proof of theorem somehow needed to move to make the thing to be local. Then in the local thing, you can deform your theory. You deform so much, you deform to Eisenstein series. Once in the Eisenstein series, everything can be computed by hand. Then this constant can be computed. So this is very important to treat as Eisenstein series. But Eisenstein is non-holomorphic, so weight 0. For proof and for application to Andreev-Otto conjecture, I will not explain that. So somehow I want to use a different language. Because where it's probably easier. So what do I mean now holomorphic form? So again, we started with the form phi f. Let me see. Start with f. So this is a form of weight. I want to say 2, 2, 2, and 0, 0, 0. In 0 here, I needed to insert. Since the weight is 0, there's something else needed to specify. I need to specify the eigenvalue. The eigenvalue, I will explain a little bit later. Eigenvalue is what? It's just eigenvalue is 1/4 plus t1 square, 1/4 plus tn square. So I explain what do I mean right on the blackboard. So I really mean that. So recall that this x or x and k, x0 n is defined to be this one. Gf plus h of g times g of f of u. Okay, u and k. So somehow I cut these as two pieces. One is g minus n, one is n. Okay, so I make my thing to be two places. So a form of this weight 222,000 really means a form. I only take a dz1, dz, the first gn minus 1. Okay? This is a form. I don't take the back. I want this one to be a form. Or one form, I mean the g minus 1 n form on x naught of n. Right? Does it make sense? Then I want to be holomorphic in this the first gn minus 1 variables. Of course, it will not be very, I mean, if will not be, it can be holomorphic again for other variable. If it's not holomorphic, then what do? I need to check how much away from holomorphic. So I apply Laplacian operate. So for I, let me see. For this I belong to this next. So I define the operate square, this get dy square. So I want to make it a positive operator. So let this be Laplacian. So you have Laplacian of this f. I mean, of course, at a place of the second one. So this is 2, 2, 2. This is 0, 0. So maybe I indexed by this is 1, 2, n. So I have Laplacian I be 1/4 plus t square of f. So now this way I can normalize this in. So this is the form it started with. It makes sense, completely makes sense. Not only that, I want f be even for the last n variables. The reason is otherwise my theory will be empty because everything will be vanished. Even means that you have this variable z goes to negative z bar. This is the operation. This is something that here write down as a t infinity. The heck operate at infinity. T negative 1 or t infinity? T negative 1, something like that. You have heck operate, you have a modular curve, you can apply the complex conjugation. This is perfect makes sense. So I can talk about new form. I can do what I had to ranking several L series. And the only thing of a gamma function, the gamma function is very similar. It's just G1 I write on the blackboard. S plus IT. This is the gamma function for TI. So it's just this kind of gamma function. Yeah, this is the error function. Error factor at infinity. So probably times G1 S minus IT for this form, for F, for this F at this non-holomorphic place. So the Gross-Zagier formula will be L1, assume that. So now I have something sigma nk. The sigma nk I have to take care of these places. So this is the places. So v divided infinity, weight equals 2. So only the first g minus n places. Join with the something v divided n. No, v inert in k, the order v of n is odd. The same thing. You have this is a function equation. So this is the function equation S chi f will be negative 1 sigma nk of nd 2 minus 2s L2 minus s chi f. The reason is because I want this one to be even. So S is even for this operator. Now what do I get? Now in the geometric side, I get a quaternion Shimura variety. So I get a Shimura variety of nk type. So it's basically same thing. You have this g of f plus this h of n. This n is exactly those places which the form is non-holomorphic of g of f, the non-holomorphic part of u. Then you get a function. Really, this is x of nk. The Zagier lines plus all the theory. I mean, these people, Vas-Piaget, Tano, and Gross, Prasad, many people's work this f will be get a function, an x of nk to the complex number. It's purely a function. Then you get your formula will be 2 to the g plus n. So this is why I keep my 1 there. It's very important. So I can recognize my dimension variety. Divide by square root norm of d. So f square, or f square not be, now you can define, you cannot use differential form anymore. You better to define by classical using the Poincare, is some metric there. Times exactly same thing, the form x chi is f prime, this pairing divided by norm of prime square. And of course you have CM points, where I mean when I write this one, you have to specify your CM points. The CM points is the same. It's g of f over u divided by t of f. And in this case, when n is non-trivial, is big, that's actually this is embedding. So this is completely fine. So maybe I mean usually in the lecture you need to prove some theorem, right? I mean at least we want to prove something, and the only thing I know how to prove that directly on the blackboard is f is Eisenstein series. So when let me say f is Eisenstein series, so what I mean, so f is E of Sg equal to summation CD z square modulo positive negative 1, and C of D is non-zero. Okay, then you get C Z plus D to S1, right? You want a real part of S is bigger than 1 to make this thing to be convergent. This is Eisenstein series. So now I pick up a K. This is the simplest thing I can do. So my K, of course, what's the simplest one? The Q of I. My chi is trivial. So I have only the modular curve I get x is upper plane modulo SL2z. Okay? So where's my Hingham divisor? For Hingham divisor, the x chi so complicated, just I. Right? You have T clause number 1. You see, you get this one. That's only the Hingham divisor you get. Now, where I compute this thing. Well, now there's a lot of things, a lot of interesting things happen. So what's the Rankin-Selberg of this thing? Well, first of all, we need to check. So now this S is not nice. So I have to change this S to be different name because I need the S to be variable for error function. Let me check this. Write this one as a which variable is better? Sigma. Okay. So how to evaluate this square root negative 1 and its Eisenstein series, sigma, and z, right? This is Eisenstein series. So this is nothing. It's just a summation of CD, then put inside CI plus D to S. So can you recognize this? What this thing is? Well, this is almost, it's just 1/2 of the zeta function of k at sigma, right? Oh, there's a square here, but now you say, well, I mean, you put a formula here, there's a square here, but this side, what this side is? This is a convolution. So there's another thing, a few things here. For example, f squared and f prime squared. This f equals f prime equals Eisenstein series. So maybe you worry these two not defined. Well, anyway, they canceled. So you don't need to define them at all because the formula, they cancel each other. Okay? But actually, it's not that simple. There's a theory how to define the norm of Eisenstein series. Well, you can define by many ways. One way defined by symmetric error function. I just write on blackboard because when you compute the cusp form, you find the norm of the form is a symmetric error function. So you can do exact same thing for Eisenstein series. It's just defined to be that one. So there's no norm problem. But the convolution, well, if we compute it, so what's going on is the zeta function of the Eisenstein series of sigma, this thing of S, I forgot, it should be, let me see, should be the zeta function, the usual zeta function of S. Let me have to figure out. Well, I'm a little bit confused. I write on sigma here as 1/2 plus IT, then I know this one will be S. Okay, so S plus T, zeta function S minus T. So if you write this way, you get zeta function S minus half plus sigma. Another one is S minus T, S plus half minus sigma, right? Something like that. Then you bring this in to this side, you will find exactly the same. But this is the simplest case. The Gross-Zagier formula can be verified. You verify the formula not for cusp form, you verify for Eisenstein series. But as I said, that the next lecture I will explain that the whole proof will be eventually reduced to Eisenstein series. There you compute by hand. Okay, maybe I should stop here.